Hello everyone. In this video, I am going to talk about chapter 15, section 15.2 and 15.3. We're going to look at principle of linear impulse and momentum again, but this time we're going to look at system of particles. So other words, whatever that we're dealing with has multiple rigid body to be considered. Okay. And then let's see. Starting with we want to talk about internally what's going on. If I have a system particle that I need to deal with, keep in mind that the internal forces between particles always occur in pairs with equal magnitude in opposite direction. This means that the internal impulse sum is equal to zero. And then the linear impulse and momentum equation for the system only includes impulse for the external force. So yes, there are multiple of them, but internally they always cancel out with each other. We only need to deal with the external. In this equation, we seen it before, sort of. Now this time you have the MIVI, right? That means if you have multiple particles, you're going to do a sum of the initial momentum. And if you have multiple forces, we're going to do a sum of all the force impulse generating by the force equals to the final momentum sum of all of them. Okay. For system of particles, we can define the fictitious center of mass for n. So, in other words, we have an imaginary mass of an aggregate particle of mass m total. So this m total is the sum of all the particles in the system, and the system particles have a aggregate velocity. So Vg equals sigma mivi divided by mass total. The motion of this fictitious mass is based on motions of the center of mass for the system. And the position vector Rg equals sigma sum of mivi divided by m total describe the motion of center of mass. So when the sum of external impulse acting on the system of object is zero, then the linear impulse momentum equals simplifies to sum of MIVI1. So initial total momentum equals the final total momentum. This equation refers to the conservation of linear momentum. And then conservation of linear momentum is often applied when particles collide or interact. When particle impact, only impulse force cause a change of linear momentum. So let's take a look at some examples together. I have a spring constant. I have this block A attached to a spring. Spring constant is 10 kilonewton per meter, and MA equals 15 kilogram. VA equals 0, so meaning block A initially is at rest. And then I have the block B, 10 kilogram coming from the right, velocity B equals 15 meters per second. And the block coupled together at impact, they stick together after they have an impact. We're looking for the maximum compression of the spring. So initial momentum, total momentum equals the final linear total momentum. Initially, A is not moving, so that means A mass times velocity equal to 0. So I only have the mass times the velocity for the block B. Since block B coming from the right, you will have 10 times negative 15 on the I direction. Afterwards, they stick together. You can look at two particles as one. So 15 plus 10 times velocity VI. And then this, we have one equation and solving for that one unknown. That tells me after the collision velocity together equals negative 6 meters per second. Negative sign means that they're moving to the left together. Next equation will be energy conservation equation. Initial total energy, which includes the kinetic energy. This is talking about after the collision, after they move together, after they stick together, right, and then keep moving to the left and compress the spring, right. This is saying, hey, after that, I have this much kinetic energy. This should be a square, by the way, 1/2 mv squared. I have this much kinetic energy. And if all this kinetic energy is used to compress the spring, how much of distance of the spring can be compressed? So this is your kinetic energy of these two moving together. And then the right hand side, all of this energy becomes the potential elastic potential energy. That's one half spring constant times the distance. This will help us calculate the distance, maximum the spring being compressed. Excuse me. Example number two, I have two cars, rail cars. We know their mass, we know their velocity, they are coming into each other. So we're looking for the speed of car A after collision if the car collides and rebounds such that B moved to the right. So in other words, B starting with coming to the left 1.5 meters per second. After they collide with each other, B moves to the right with a speed of 2 meters per second to the right. Initially, this thing is to the left. Okay, so initially you have negative velocity, not negative, but negative velocity, meaning I'm going to the left. We're looking for the final impulse force between the cars if the collision take place in zero point 0.5 seconds. So initial linear momentum, I have initial linear momentum for A, initial linear momentum for B. That will equal to the final linear momentum. I don't know how fast VA velocity for the A will be, but we can calculate it. We know the velocity of B is going to the right 2 meters per second. Initially it's negative 1.5 to the left. So there's my initial linear momentum equals the final linear momentum total. So initial total, final total. This will help us calculate how big is the velocity A after the collision. And then we're looking at A only. For the particle A, initial linear momentum plus the impulse equals my final linear momentum. Initial linear momentum plus the impulse equals the final um, linear momentum. Initial we know, final we know as well because we calculate the velocity from the previous step. And then this will help us calculate how much impulse, which is force over a short period of time, how much linear impulse do we have. Okay, the unit will be Newton meter, Newton second, force times time. And if we know this will happen within zero point 0.5 second, total time is half a second, we can calculate the average. Average force when they collide together is 105 kilonewton. I am going to skip group problem number one. It's for you to look at yourself. And I will talk about group problem number two as our last example today. The two rail cars, A coming to the right, B coming to the left. They are going to hit on each other, right? They're going to have a collision. We're looking for the maximum compression of the spring mounted on car A. So initial linear momentum equals your final total, right? Initial, I got A, I got B. We're going to do our unit conversion. The velocity is given to us in kilometers per hour. We're going to convert all of them to meters per second, both of them. Okay. VB is coming to the left. That means I have negative velocity. So initial, I have MAVA, and then MVVB is, since the VB is the velocity of V going to the left, it's a negative, right? So this is my initial linear momentum for A and B. And then later they stick together, okay? And this will help me calculate what is the velocity after they stick together. And then we're going to write an equation for energy equation. After they stick together, the velocity that we calculated is this much, 2.778. Okay, so that means when we're looking at from the energy perspective, initial total energy equals the final total energy. Initially, I have kinetic energy from A, kinetic energy from B, and there's no compression on the spring, so there's no potential energy. But afterwards, they move together. This term refers to, see, 45,000 is 30,000 plus 15,000, right? So these two together. So this is going to be these two together, stick together, the total kinetic energy plus the spring is being compressed, right? Compression on the spring. So that means there is some elastic potential energy on the spring. So 1/2 times spring constant times the S max square. This will help me maximum compression of the spring. So maximum, um, maximum spring elastic potential energy. Okay, that's all that I want to share with you in this video. Thank you for watching. Hope you find this helpful.